Welcome to this coding walkthrough. In this session, we'll explore LeetCode problem number 187, repeated DNA sequences. This problem challenges us to identify DNA sequences in a string that occur multiple times, a great exercise in string manipulation and hash maps. Let's dive in. The problem asks us to find all 10-letter-long substrings in a given DNA sequence that occur more than once. The DNA sequence is represented as a string S, and it only contains the characters C, G, and T. The task is to return these repeated substrings in any order. For example, if we are given the input string S equals AAACCCCCAACCCCCAGGGTTT, we need to identify all 10 character sequences that appear at least twice in this string. In this example, the output is AAACCCCCCCCCAA. Here's why: the DNA sequence contains the substring AACCCC twice, and similarly, the substring CCCCCAA also appears twice. Both of these meet the condition of occurring more than once, so they are included in the output list. The list can be returned in any order. Now, consider a simpler input, S equals AAAAAAA. Here, the substring AAAAAA appears 3 times in the sequence. Since it repeats, the output is AAAAAAAA. To further clarify, in the second example, the substring AAAAAAA is the only 10-letter-long sequence that occurs multiple times in the input string. As a result, it is the sole element in the output. Now, let's discuss some important constraints. The length of the input string S can be as large as 100,000 characters, which means our solution needs to be efficient and handle large inputs within the given limits. Additionally, the string is guaranteed to consist only of the characters C, G, and T, representing a valid DNA sequence. Finally, let's look at some edge cases. If the input string has fewer than 10 characters, it's impossible to have any 10-letter substrings, so the output should simply be an empty list. Similarly, if all 10-letter substrings in the sequence are unique, the output will also be empty because no substring repeats. On the other hand, if there's only one substring that repeats multiple times, like an S equals AAAAA, the output will contain just that substring. For very large strings, the algorithm must be optimized to process the input efficiently. Lastly, if the string is made up of a single repeated character, such as S equals AAAAAAA, the result will be a list with just that repeated character sequence, like AAAAAA. These considerations are key to understanding the problem's nuances and edge cases. To solve the problem of finding repeated DNA sequences, we first consider the brute force approach. The intuition behind this method is straightforward. We generate all possible 10-character substrings from the input string S and count how often each substring appears. To do this, we can use nested loops or slicing to extract each substring one by one. These substrings are then stored in a dictionary or hash map, along with their frequencies. Finally, we simply iterate through the dictionary to identify substrings that occur more than once. However, while this approach is conceptually simple, it is not efficient. The time complexity is n squared, as generating each substring and processing them involves quadratic time for a string of length n. Additionally, the space complexity is n, since we need to store the substrings and their counts. This approach also suffers from redundant computations because overlapping substrings are processed multiple times, making it impractical for larger inputs. To improve efficiency, we can use an optimized sliding window technique combined with hashing. The intuition here is that a sliding window of size 10 allows us to efficiently generate substrings without redundant computations. Instead of recalculating the entire substring for each position, we simply slide the window one character at a time. As we generate each substring, we store it in a scene set. If a substring appears again, we add it to a separate repeated set. At the end, converting the repeated set to a list gives us the result. This approach significantly reduces time complexity to n, as each substring is processed in constant time. However, the space complexity remains n, because we still need to store the substrings in sets. While this method is more efficient than brute force, it can still consume considerable memory when dealing with very large strings. To address this, we can take optimization further by using bitwise encoding. The bitwise encoding approach leverages the fact that DNA sequences only contain 4 characters, A, C, G, and T. Since each of these can be uniquely represented using just 2 bits, we can encode any 10-character substring as a 20-bit integer. This allows us to work with compact numeric representations instead of full substrings, saving significant memory. The process involves mapping the characters A, C, G, and T to integers, such as A equals 0, 0, C equals 0, 1, G equals 10, and T equals 11. Using bitwise operations, we compute a hash for each 10-character substring and store these hashes in sets to detect duplicates efficiently. This method has a time complexity of O, n, as each hash is computed in constant time, and the space complexity remains O, n, but we store hashes instead of substrings. This not only reduces memory usage but also improves speed due to the simplicity of bitwise operations. However, it does require a deeper understanding of bitwise manipulation, making the implementation slightly more complex. The chosen strategy for solving this problem is the optimized bitwise encoding approach. This method strikes a balance between efficiency and memory usage, making it the most robust solution. By leveraging the fixed alphabet size of DNA sequences, we can encode substrings compactly and detect duplicates more efficiently. One key observation is that the limited alphabet of A, C, G, and T makes bitwise encoding particularly practical. Additionally, the sliding window ensures no redundant computation of substrings, maintaining linear time complexity. While this approach introduces some implementation complexity due to bitwise operations, the trade-off is well worth it. It provides significant memory savings compared to storing entire substrings and scales efficiently for large input sizes. Ultimately, combining the sliding window technique with bitwise encoding results in a solution that is both fast and memory efficient, making it ideal for tackling this problem. To solve the problem of finding repeated DNA sequences, we need to identify all 10-character long substrings in a given string S that occur more than once. This is particularly useful in analyzing DNA sequences, where identifying repeated patterns can reveal significant biological insights. First, we validate the input to ensure the string has at least 10 characters. If not, we return an empty list since no valid substrings can be found. Next, we initialize two structures, a dictionary frequency to track the frequency of each 10-character substring and a list result to store substrings that appear multiple times. To efficiently extract these substrings, we use a sliding window of size 10. As we iterate through the string, we extract each 10-character substring, check if it exists in frequency, and update its count accordingly. This approach avoids recalculating substrings repeatedly, making it more efficient than a naive method. In the sliding window process, if a substring is already in the frequency dictionary, we simply increment its count. After constructing the frequency dictionary, we filter the results by iterating through it and appending any substring with a count greater than 1 to the result list. Finally, we return this list of repeated substrings as the output. For example, consider the input string S equals AAGGGTTT. Using the sliding window, we generate substrings such as AACCCC, AACCCCA, AACCCCA, and so on, for all valid positions in the string. Each substring is added to the frequency dictionary, where its count is updated as necessary. This method ensures that we check every 10-character substring efficiently, avoiding redundant computations. Once the sliding window traversal is complete, the frequency dictionary contains the occurrence counts of all 10-character substrings. For example, we might have frequency equals A2, A2, C1, C1. To extract the result, we filter this dictionary to find substrings with a count greater than 1, producing a final list of repeated substrings like AAACCCC, AACCCCA. This output represents the substrings that appear more than once in the input string. The key insight here is the efficiency of the sliding window approach, which avoids the overhead of nested loops by maintaining a fixed window size and moving it one character at a time. This makes the process linear in time complexity, which is crucial for analyzing large strings. The sliding window technique is a cornerstone of this algorithm, allowing us to extract substrings in O(n) time by reusing most of the computation for overlapping substrings. This is far more efficient than generating all substrings naively, which would take O(n²) time. The use of a dictionary for frequency counting is another critical component. Dictionaries, or hash maps, offer average O(1) time complexity for inserts and lookups, making them an ideal choice for tracking substring frequencies. Additionally, this approach naturally handles edge cases, such as strings shorter than 10 characters, by returning an empty result immediately. Overlapping substrings are also seamlessly accounted for, as the sliding window inherently captures all possible substrings of the required length. The use of these data structures, dictionaries for counting and lists for storing results, ensures both efficiency and simplicity in implementation. Analyzing the algorithm's complexity, the time complexity is O(n). This includes O(n) for generating substrings using the sliding window and O(1) on average for each dictionary operation, resulting in linear time overall. The space complexity is determined by the dictionary and result list. The dictionary requires OK space, where K is the number of unique 10-character substrings, and the result list requires OR space, where R is the number of repeated substrings. Thus, the total space complexity is OK plus R. For further optimization, a rolling hash technique like Rabin-Karp can be used to represent substrings as integers, reducing memory usage by avoiding repeated storage of string data. This is particularly advantageous when working with very large strings, as it minimizes the algorithm's memory footprint while maintaining its efficiency. This Python implementation solves the LeetCode problem number 187, repeated DNA sequences, by efficiently identifying all 10-character long substrings in the given string that occur more than once. The function findRepeated DNA sequences takes a single input string s. First, it initializes two sets, seen to keep track of all 10-character substrings encountered so far, and repeated to store substrings that have been seen more than once. The function then iterates through the string using a sliding window approach. The range of the loop is len s 9 because we need at least 10 characters to form a valid substring. For each index I, it extracts the substring s, I plus 10. If the substring is already present in the scene set, this indicates it has been encountered before, so it is added to the repeated set. If not, the substring is added to the scene set. Finally, after processing the entire string, the function converts the repeated set into a list and returns it. This ensures that the result contains only unique repeated sequences. The use of sets for seen and repeated ensures efficient membership checking and avoids duplicates. The algorithm has a time complexity of O(n), where n is the length of the string, as we process each character exactly once in the sliding window. It also has a space complexity of OK, where K is the number of unique 10-character substrings in the input string. This is the Java implementation of LeetCode problem number 187, repeated DNA sequences. It mirrors the logic of the Python solution, using Java-specific collections like hashset for tracking scene and repeated sequences. The method iterates through all 10-character substrings of the input string s, adding repeated substrings to the result set. Java's substring method is used to extract substrings, and the final result is returned as a list. To start solving the problem, we first define the input string s as AAAACCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCCC in this string. We begin by initializing two sets, seen to keep track of substrings we encounter during the process and repeated to store substrings that we find more than once. The main logic involves iterating through the string, extracting substrings of length 10. The loop runs from I equals 0 to len s 10, which in this case is 20. This ensures we only consider valid 10-character substrings without exceeding the bounds of the string. As we iterate through the string, we process each 10-character substring one by one. At the first index, I equals 0, the substring is AAAACCCCC. Since it's not already in the scene set, we add it to scene. Moving to I equals 1, the substring becomes AAACCCCCA, which is also new, so we add it to scene. This process continues, with each new substring being added to scene until we reach I equals 10. At this point, the substring AAAACCCCC reappears. Since it's already in scene, we add it to the repeated set. Similarly, at I equals 11, AAACCCCCA is encountered again and is added to repeated. Finally, we convert the repeated set to a list, resulting in the output AAACCCCC. Now, let's consider a different scenario where the input string is ***. Here, the goal remains the same: find 10-letter-long substrings that repeat. We begin by initializing the scene and repeated sets. This time, the length of the string is exactly 10, so the loop runs only once, starting at I equals 0. The single substring extracted is ectac, which is added to the scene set because it hasn't been encountered before. Since there are no additional substrings to process and no repeats, the repeated set remains empty. Converting this to a list gives us the final output, an empty list, indicating no repeated sequences were found. In this example, we examine the case where all characters in the input string are identical. The string provided is AAAAAAAAAAA, and we're tasked with finding repeated 10-character substrings. As before, we initialize the scene and repeated sets to empty. The loop runs from I equals 0 to I equals 2, allowing us to extract 3 substrings of length 10. At I equals 0, the substring is AAAAAAA, which is new, so we add it to scene. At I equals 1, the substring is again AAAAAA, but this time it's already in scene, so we add it to repeated. At I equals 2, the same substring appears again, but since it's already in repeated, no changes are made. This results in repeated containing just one substring, AAAAAAAA. Finally, we convert the repeated set to a list, giving us the output AAAAAA. This demonstrates that even in a string where all characters are the same, the algorithm successfully identifies repeated 10-character substrings. This example highlights how the solution handles edge cases where repeated sequences are highly uniform. Here, we analyze the time complexity of the algorithm used to find repeated DNA sequences. The algorithm has a time complexity of O(n), where n is the length of the input string s. Let's break this down step by step. First, the algorithm iterates through the string, generating all possible 10-character substrings. This involves iterating from index 0 to len s 10, which results in len s 9 iterations. Extracting a substring in Python is efficient and takes constant time, or O(1), for each operation. Next, for each substring, the algorithm checks if it exists in the scene set and possibly inserts it into either the scene or repeated sets. These operations, membership checks and insertions, are also O(1) on average since sets in Python are implemented as hash tables. Combining the substring extraction and set operations, we process len s 9 substrings, leading to a total cost of lens 9, which simplifies to O(n) in the average case. Now, let's consider the space complexity of the algorithm, which is O(n) in the worst case. This arises primarily from the storage requirements for the scene and repeated sets. In the worst case, all substrings of length 10 are unique, meaning the scene set stores all len s 9 substrings, contributing O(n) storage. Similarly, the repeated set stores only duplicated substrings. If all substrings are repeated, this set could also grow to O(n). Additionally, each substring of length 10 requires O(10) memory, which simplifies to O(1), but since there are O(n) substrings processed, this contributes an additional O(n) to the total space usage. When we combine these factors, the overall space complexity remains O(n). Finally, let's analyze the algorithm across different cases. In the best case, if the input string s has fewer than 10 characters, no substrings are processed, and both the time and space complexity reduce to O(1). In the average case, for a random string of length n, the algorithm processes n 9 substrings, maintaining time and space complexity at O(n). In the worst case, where all substrings are either unique or repeated, these complexities still remain O(n). Comparing this to a naive approach, which compares all pairs of 10-character substrings, the brute force method would require O(n²) time due to approximately O(n²) substring comparisons. The optimized approach, on the other hand, avoids redundant comparisons by leveraging hash-based sets for efficient substring tracking, reducing the time complexity to O(n). Mathematically, slicing a substring and set operations are O(1) on average. With O(n) iterations for substring processing, the total time complexity is O(n). Similarly, since the space required is proportional to the number of substrings, the space complexity is also O(n). This makes the algorithm both time and space efficient compared to naive alternatives. When tackling this problem, there are a few common pitfalls to watch out for. First, failing to consider edge cases where the input string is shorter than 10 characters can lead to unnecessary computations or even runtime errors. Since a 10-letter substring can't exist in such cases, it's critical to handle this scenario upfront. Another mistake is using nested loops to generate substrings, which results in a time complexity of n squared. This approach is highly inefficient for larger inputs and often leads to time limit exceeded errors. Additionally, incorrectly identifying unique sequences is another frequent issue. Without an efficient hashing or set-based approach, you may either miss some duplicates or mistakenly count non-repeated sequences. Lastly, when using advanced techniques like rolling hash or bit masking, improper handling of hash collisions can lead to incorrect results. It's important to ensure that your method accounts for these collisions to maintain accuracy in detecting repeated sequences. Now, let's address space optimization for large inputs. Directly storing all substrings in memory can quickly become a problem when dealing with very long strings. To address this, efficient hashing or bit masking techniques are crucial, as they help reduce space complexity significantly. From an interview perspective, this problem is a great example of rolling hash or fixed window substring questions, which are quite common. Mastering the sliding window technique is key to solving these efficiently. Interviewers may also focus on optimization, so it's important to aim for a solution with n time and n space complexity. Be ready for follow-up questions that extend the problem, such as finding repeated substrings of length k instead of 10, or working with different character sets like binary or hexadecimal. Lastly, understanding the trade-offs between a brute force approach and optimized solutions is essential. While brute force is simpler, optimized methods offer much better performance for larger inputs. This problem also connects to a number of related challenges, which can help deepen your understanding of substring processing. For instance, LeetCode 3, longest substring without repeating characters, is a classic example that emphasizes sliding window techniques. LeetCode 76, minimum window substring, is a more advanced variation that requires careful handling of substring searches. LeetCode 438, find all anagrams in a string, deals with fixed-length substring searches using hash-based techniques, which is directly relevant here. Similarly, LeetCode 30, substring with concatenation of all words, is another substring problem, but with added complexity that demands both space and time optimizations. Studying these related problems can help you build a strong foundation for tackling similar questions in the future. Lastly, let's compare some alternative approaches and their trade-offs. The brute force approach, while simple to implement, has a time complexity of n squared and a space complexity of n for storing substrings. This makes it impractical for larger inputs due to inefficiency. A hash-based sliding window approach improves on this, offering n time complexity and n space complexity. It's much more efficient for larger strings but requires careful implementation to avoid issues like hash collisions. For even greater space optimization, bit masking can be used, particularly for DNA sequences or fixed small character sets. This approach achieves n time complexity with a remarkable 1 space complexity for storing the bit mask. However, it's less intuitive and limited to specific use cases, making it less flexible compared to other methods. Choosing the right approach depends on the problem constraints and the trade-offs you're willing to make between simplicity, efficiency, and adaptability. Great job completing this walkthrough. Today, we tackled repeated DNA sequences and highlighted the use of sliding window and hash maps to solve substring problems efficiently. Remember, mastering these techniques will help you in many coding challenges. Thanks for watching, and see you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!